Hello, good morning, good afternoon, and welcome. I'm very pleased to be joined by Allen Reid. Allen's the commercial director at NANOGAP, a very interesting company doing some amazing IP development in the area of hydrogen. And you're going to be speaking at next week's World Hydrogen Congress in North America in Houston. You're a strategic partner of the event. So welcome, Allen. Thanks for joining me.
Thanks, Nadeem. Nice to meet you.
So your background is obviously chemical engineering, chemistry. I know you're based there in Portugal, in Santiago de Compostela. You're a spin out in Spain. Sorry, and you're a spin out of the university there. Can you give us a little bit of a background to the technology that NANOGAP are working on? It's pretty complex, but it sounds fascinating, and it also has a very unique application as far as I can see.
Yeah, sure. So NANOGAP is developing what we call metal molecule technology. Previously, we've called it atomic quantum clusters, but basically we take an element like silver or copper, which is a metal, and we make particles so small, just a handful of atoms, say 5 atoms, for example, that they have no metallic properties. The electrons are confined into discrete energy levels, quantum confinement, and due to that different electronic structure, different chemical structure, we get very different properties from the bulk material or even conventional nanoparticles. The main properties that I'm involved in developing are the catalytic properties, which includes photocatalysis, thermocatalysis, and electrocatalysis.
Right. And what is a specific application and with regards to hydrogen?
Okay, so in hydrogen, we made a breakthrough a few years ago. So if you take a standard metal molecule, it absorbs in the UV part of the spectrum and can be a UV activated photocatalyst, similar to a conventional photocatalyst, for example, titania, which is also a UV absorbing photocatalyst. But we discovered when we put the metal molecule on the surface of titania particles, we get all sorts of different electronic transitions between the two species. And this has 3 big effects. The first is that it increases the level of absorption, and it moves the absorption into the visible part of the spectrum. So we're able to capture much more energy from sunlight from the whole solar spectrum compared to each species on its own. Another benefit in having 2 species is that we separate the charges. So when we absorb the energy, we create a positive hole and an electron, and that's the species that we can do reactions with. We keep them apart in the 2 separate species, preventing recombination. So all of those benefits in terms of enhanced absorption in the visible, preventing recombination of charges, resulted in 3 orders of magnitude improvement in the efficiency of the photocatalysis. And what we discovered with just visible light and sunlight is we could split water to produce hydrogen and oxygen.
Yeah. So the photocatalysis of water to produce hydrogen.
Yeah,
and that's and you were explaining before through the use of heat and putting the process through an initial stage of concentrated solar power.
Yes. So we developed a technology further into what we've called photothermal looping catalysis, which is basically oxygen vacancy driven catalysis, which is not a new process. It is a process that's practiced industrially, but the problem with it is it operates at temperatures up to 1500 degrees centigrade. With our photothermal metal molecule-based catalysis, we have reduced the operating temperature to 500 degrees centigrade or less. And those temperatures can be achieved by concentrated solar power technology. So we harvest the light and concentrate it into our photoreactors, and we perform a 2-stage process. The first stage is using the light and the heat that we collect through CSP to generate oxygen vacancies in our catalyst, which is a very efficient process. And then the subsequent process from that, we introduce steam in the water. The oxygen from the water refills the vacancies, producing hydrogen. And this is a very efficient process. Theoretical efficiencies, solar to hydrogen efficiencies of up to 77%. And then when we consider the whole integrated system with the concentrated solar power part, we can still achieve 42% solar to hydrogen efficiencies, which compares very favorably to the 11%, which is typical for photovoltaic electrolyzers.
So yeah, I mean, from 42% as opposed to 11%, and have you taken that through and sort of modeled the potential, capex expenditure for a commercial system?
Yes, we have. Just to give an example of a 1 megawatt equivalent photovoltaic electrolyzer unit. So the equivalent for our system, the capex would be almost half for the equivalent electrolyzer PV system. OPEX would be almost half what it would be for that PV electrolyzer system. And another great advantage is that the footprint, the space that it actually takes up, is 8 times less for the corresponding photovoltaic electrolyzer system.
Yeah. Sounds amazing. And in terms of whereabouts are you in your technology development cycle, or I guess technology readiness level?
Well, we've created a spin out called Hysun to develop this technology. It's in partnership with a company called Chua Engineering, which is a leading concentrated solar power company. They've built some of the biggest CSP plants in the world, in China, in the US, in South America, in Europe. So they're a leading CSP company, and the joint venture Hysun is between NANOGAP and Chua Engineering. We provide the catalyst technology. Chua is providing the CSP technology, and Hysun will build the photoreactors and build the integrated plants. So right now we're on a 3-year plan to take the technology to TRL 9. Currently we've got lab scale reactors that's generating data that we're using to further develop the process. In 3 years' time, and with $15 million, we'll take it to the 1 megawatt equivalent that I was talking about earlier. So that's a plant that will produce 46 tons of hydrogen a year at 18 kilograms an hour, equivalent to the 1 megawatt electrolyzer plant.
Yeah, that's pretty impressive. Pretty impressive numbers, and certainly pretty rapid progress to go all the way up to TRL 9 in 3 years, and potentially, if it works, it's potentially very disruptive.
Yes, yeah.
And in terms of the the projects, you're obviously in coming to North America for a reason. Can you tell us a little bit about the sort of commercial side to the business, and what you're looking to do? Are you looking for partners and other people to help you develop the technology? Yeah,
well, I'm coming to North America representing NANOGAP. So the Hysun technology for the production of 100% renewable hydrogen is something NANOGAP is developing the catalyst for, and we have Hysun that's in place to develop the hydrogen production process. But NANOGAP's catalyst can also be used for different applications related to hydrogen. And during my talk on Tuesday, I'll be talking about those. So I'll tell the story behind hydrogen, which I've described to you very briefly.
Yeah.
We can also use the same process, this photothermal looping catalysis I was describing earlier, as a potential for a very broad number of applications. So we can use the same fundamental process for CO2 valorization. And we're thinking where industry would be most interested in this is to make renewable syngas. So we convert carbon dioxide to carbon monoxide. And if you run that process in parallel to the Hysun hydrogen process, then you would have 100% completely renewable syngas. And that could be a major benefit to the process industries. Methane valorization as well. We can do oxidative coupling of methane to make higher value C2, C3 compounds. We do partial oxidation of methane, another route to carbon monoxide and renewable syngas. And all of this can be done at the temperatures I mentioned earlier, 300 to 500 degrees centigrade, significantly less than the standard industrial processes used to make, for example, syngas at the moment, which can be up to 1450 degrees centigrade. So we think there's huge efficiency benefits to developing this technology in a broad range of applications.
So for that sort of technology path, how easy is it to scale up from say the 1 megawatt?
Well, this is a completely modular system, off-grid modular system, and so the 46 tons a year plant, the 1 megawatt equivalent size, is just the starting point. When we commercialize the technology, we're planning on building 15 times that scale and 200 times that scale. So that's going to be plants that produce around 700 tons a year and 9,000 tons a year. And operating at that scale and with the efficiency benefits that I talked about earlier, then we can really start to get towards the cost and price of grey hydrogen. So we think for that intermediate type plant, the price, the cost can be less than $3, maybe $2 to $3 per kilogram. And for the 9,000 tons a year plant, then we're starting to get close to the $1 a kilogram cost price point of grey hydrogen. And that's very important, because that's not only important for the developing a renewable fuel source with no carbon footprint, but it also means you can start to use hydrogen as a chemical feedstock for production of chemicals like ammonia and methanol and others. So this is, the scalability of it being based on a modular design off-grid is very easy.
Well, thanks a lot, Alan. That's been fascinating. Certainly sounds like really, really incredible technology, and you're going to have a lot to do over the next 3 years to scale it up. And we certainly look forward to helping NANOGAP along the way. And so, we're going to be watching very carefully, and we look forward to hearing more about NANOGAP next week at the World Hydrogen Congress in North America. So many thanks, Alan.
Thanks very much, Nadeem. It's a pleasure talking to you.
Yeah. Cheers. Take care.
Cheers.